Okay, so this is lecture 32. I want to talk to you a little bit about the concept of a conservative vector field. So this is one of the big theoretical topics in Calculus 3, and really most of the interesting theorems in this course have something to say about this question, about this discussion. So first order of business is for us to, state the fundamental theorem of calculus for line integrals. And here it is. It's the following. If we integrate a gradient, right, of a potential function f over a curve, if that curve, and here's a picture of it, so think of it like this. Here's the curve C. It starts at point P. It terminates at point Q. All right. Then, excuse me, the integral of the gradient of f over that curve C will be the value of the function being, gradiented. Sorry, not something I usually say. It'd be f of q minus f of p. So this is the fundamental theorem of calculus for line integrals. The proof of it is here. So starting with the integral of the gradient, by definition, that's the gradient evaluated at the parameterization, dotted with the velocity, right? But then by one of our chain rules, that's exactly the derivative of the function evaluated at the parameterization of the curve dt. But then, remember calculus 1, if we integrate a derivative, we just, by the total change theorem, we take, f of r of the upper bound minus f of r of the lower bound. Usually it's called the net change theorem, right? But and then, of course, r of b is q, and r of a is by assumption p. So there you go. That's the fundamental theorem of calculus for line integrals. And it basically just rests on the fundamental theorem of calculus from calculus 1, as well as the multivariate chain rule. Very simple. Now, that brings us to define a certain kind of vector field. We say that if U is a subset of Rn, so U is usually I often think of an open set. It could be an open subset of Rn. Then I'm not committing to that. I'm saying U is some subset of Rn, all right? Then we say f is conservative on U if there exists a potential function f such that f is the gradient of little f. So the vector field f is the gradient of the potential function f on U. Moreover, if f is conservative on its domain, then we just say that f is a conservative vector field. All right, and so here's an example calculation of one. If a vector field is conservative, it's often pretty easy to find the potential function. In retrospect, I think that's some of the homework I've asked you, basically. So if I have the vector field 2x, 2y, 3, we can show that this is in fact conservative on R3. Oh man. Oh, well, here it is. Here's the potential function, x squared, y squared, 3z. If I add those together, calculate the gradient of that function, we get 2x, 2y, 3. And that's true for any point x, y, z, so therefore we have shown that this vector field, 2x, 2y, 3, is in fact conservative on all of space in 3 dimensions. And so then by the fundamental theorem of calculus, if I have a curve which goes from the origin to the point ABC, right? Doesn't matter what the details of that curve are, then the integral of f dot dr, the line integral from the origin to ABC, is just f of ABC minus f of 0, 0. In other words, it's a squared plus b squared plus 3c. And we didn't even need to know what the details of the curve were, right? We didn't need to know if it was a line segment, or if it was a twisted cubic, or whatever. Could have been anything. See, if you go from the origin to the point ABC, like this math says that this force field F, it does the same work if you take it like on this path versus this path. Whee! Like it doesn't matter which path you go from the origin to ABC, the same amount of work is ultimately done by this force. All right? It's a conservative force. Now, why do we call it conservative? Let me address that question. So the key is this little identity here. If we calculate the derivative with respect to time of 1/2 mv squared, that's the derivative of 1/2 mv dot v. By the product rule, that's dv dt dot v plus v dv dt. In other words, that's the acceleration dot the velocity plus the velocity dot the acceleration. So you have twice two of them, and so 1/2 mv squared is actually the mass times the acceleration dot the velocity. And so with that in mind, if we have the net force, right? If we have the net force on a mass, then Newton's second law says F is equal to ma. So if C is a curve from R1 to R2, and our force is is the net force, right? Then F dot dr is F dot v, right? dt, that's the definition. But F was equal to ma if we're assuming Newton's second law holds, right? So you have ma dot v, and by our little identity, that's the derivative of 1/2 mv squared. But then by the net change theorem, that's 1/2 mv squared at time 2 minus 1/2 mv squared at time 1, where we've defined, and so I just say it's k of t2 minus k of t1, where we've defined k as 1/2 mv squared. Of course, this is the so-called kinetic energy from physics. And this little calculation right here shows you that the work done by a force, if it's the net force, right, it has to be the net force, but the work done by the net force is equal to the change in kinetic energy. And this is true for any net force. It doesn't matter if it's conservative or not. And this result is called the work energy theorem. All right. It does not require that the function is conservative. However, if the function is conservative, then we get to say more. See, because if the function is conservative, then we get this additional calculation that the integral of f dot dr is the integral. And by the way, in physics, we put a minus. F is equal to minus the gradient of the potential energy function, which I'll use a big U for here. U equals potential energy. And the reason for the minus will become apparent shortly. So we don't bother with the minus in math because we just have gradient of F is equal to the vector field F, you know, because we don't care about that minus. But physicists care about it because when you calculate here, you get U of R2 minus U of R1. And so if the net force is conservative, then this should be equal to that, right? And so if you bring all the two things together and all the one things together, you get that k1 plus u1 is equal to k2 plus u2 if you put that minus in, right? So putting that minus in is what makes the energy, which is k plus u, be the same before and after the process, right? In other words, total mechanical energy is conserved. So if we want the total mechanical energy to be kinetic energy plus potential energy, then we have to put the minus here to be consistent with that. So the convention in physics is to put the minus here for potential energy. But anyway, that's the work energy theorem, and that's why we call it a conservative force, because conservative force being the net force means that the total mechanical energy is conserved. Now, so the next order of business is to discuss what are other properties of conservative forces. They actually have a number of interesting properties. So one of those properties is path independence. Here's a definition. If u is a subset of Rn, we say f is path independent on u if the integral of c1 is equal to the integral of c2 for each pair of curves c1 and c2 and u beginning at p and terminating in q. Like here's a picture of this. U is some kind of set, it's some kind of universe of, you know, universe of discourse. And we've got point P, we've got a point Q, right? And then we have two curves, C1 and C2, and they're inside U. All right? And they both start at P and end at Q. Well, path independence says that the integral over C1 and the integral over C2, they have to be equal. If the force is path independent, it says it doesn't care whether you take C1 or C2 first. And so that turns out to be equivalent to conservative. In fact, we can say the following. And this is a list of equivalent characterizations of conservative vector fields. For a open connected subset of Rn, the following are equivalent. F is conservative. All right. In other words, number 1 is my definition. Point number 2, F is path independent on U. Number 3, the integral of the force around a closed curve, sometimes this is called a loop, the integral around a loop is 0 for all loops in U. And this is, now if we add the condition that we're looking at R3, then we can add a fourth one here. And also that we need U is simply connected, which we'll talk more about later, but then the curl of F being 0 on U is a sufficient condition to guarantee that the vector field's conservative. So the first 3 are just equivalent characterization. The fourth one we need to be in 3 dimensions, and we need U to be simply connected. And so if you want to prove 4 things are equivalent, if you can prove 1 implies 2, implies 3, implies 4, and then also that 4 implies 1, then that gives you the equivalence of all 4. But I think what I'll do proof-wise is I'll look at how to get one from the other, or I'll try to prove biconditionals wherever I can. We have to wait to prove 4 implies 1 until we have something called Stokes' theorem. We can show that 1 implies 4. That's easy. Notice that if f is equal to the gradient of f, then the curl of the gradient is 0. So 1 implies 4 is immediate from the vector calculus identity that the curl of the gradient is 0. So anyway, 1 implies 4 is easy, but 4 implies 1 is more subtle. And again, we need a theorem, and it's a deeper truth. And so the next bit of the notes, I look at the proof of a few of the other assumptions or claims. Let's see here. 1 implies 2. If the force is conservative, right, and we have 2 curves that both begin at the same point and terminate at the same point Q, then we can write the integral as the gradient of the potential function, and that's f of q minus f of p, but it doesn't matter whether we put c1 or c2 here, we still get f of q minus f of p. Like, same calculation holds for the second curve, so it follows then that this integral is equal to that integral, but c1 and c2 are arbitrary curves in the inside the set, and therefore 2 holds, so that's 1 implies 2. 2 implies 1 is trickier, and basically what this paragraph here tries to do is to explain to you how we can construct a curve. How we basically, what this paragraph does is it explains to you that we can construct the potential function using a line integral of a specific type, and the unambiguity, the lack of ambiguity in that construction rests squarely on the path independence that we're assuming. If you'd like to see the proof of this, send me an email. I can try to find you where I've done it before in the other course. It takes me about a half hour to do this justice. 2 implies 1. 2 implies 1. What? That feels wrong. This was 2 implies 1. I think that's a typo. Assume f is path, and I believe this is going to be 2 implies 3. 2 implies 3 would make more sense to me. Suppose f is path independent. Consider a closed curve. Yeah, this is 3. 3 is the integral around loops are 0. This is actually a good test question. Can you prove 2 implies 3? If we have path independence, if you consider so here's u again, all right? And so we've got a closed curve in C, so that looks something like this, all right? And I called that curve C, right? And then pick any pair, it says pick any pair of points, P and Q on C. I'll draw a picture of it. Oops, sorry, let me get back frame here. Any pair of points, P and Q, right? And if you do that, C's got some direction. Let's suppose it's counterclockwise for the sake of discussion. Then if you look at it, we can break that loop into two curves, right? On the one hand, you've got C1 like this, and you've got, well, you got C2 if we make C2 go the same way like that. Well, then in this setup, the loop C would be C1 union with minus C2, right? Because we have to reverse C2. But the thing is that in this context, we're assuming path independent, right? So the integral of f over C1 is equal to the integral of f over C2, right? But oh, did I labeled them the opposite way? Oh, curses. Fine. I put a, dang it. My use of C2 is opposite. So I put a plus here. Oh, man. Fine. I made this one C2, so I'll, curses. Stupid notes. An idiot wrote these. All right. Great. So C is C1 union C2. So that means that if we do that, then C1 goes from P to Q, but minus C2 goes from P to Q, if that's what C2 means. So path independence means that this is equal to that. This integral is equal to that integral, but that implies that this integral minus that integral is 0, but we can cancel this minus and that and get this integral plus that integral is 0. But this integral plus this integral is also equal to the integral of the union of the two curves C1 and C2, which is just C again. And so there you have it. We just took an arbitrary loop in the set U on which f is assumed to be path independent, and we proved that that integral around that loop has to be 0. That's the claim of 3. Integrals around loops are 0. Consequently, 3 is true. And the proof of 3 implies 2 is pretty similar. I'll just draw the picture for it down here. Here's our U, right? I'm assuming that the integral around loops are 0 this time. If I want to prove that we have path independence, think about it. Pick 2 points, P and Q, right? And pick 2 paths, right? I guess, this is the thing that's tricky, is I guess the paths could overlap, right? I'll let you think about that. What would happen if the paths overlap? If the paths intersect, then you can break it into more loops. So this is so I said C1 and C2 start at P and end at Q. So the meaning of C1 and C2 is opposite here. It's not quite the same as the last one. So if we look at C1 and C2 ending at P, starting at P and ending at Q, then in this case, like C1 union with minus C2 is a loop, right? And so the integral, and I call that loop C. So the integral around C is 0, but that's 0 is equal to this integral, which is also equal to the integral of C1 minus the integral, plus the integral of minus C2, but by then pull the minus out of the, reverse the curve to pull the minus out, and you get that. But this is equal to 0, so it follows that the integral over C1 is equal to the integral of C2. But C1 and C2 being arbitrary paths, we've proved path independence. Now, again, technically that's maybe that's a lemma, and then, really you should consider, actually it's quite horrible to what consider in general, I suppose. But students never corrected me, like, what would happen if one of the curves was like this? Right? And maybe that's C1, right? And maybe C2, this is P, this is Q, right? And what if what if C2 is like this, you know? And then it's just like, you know, oscillating smoothly. Well, that's the thing, is oscillation, if it's dense, not really smooth, is it? But anyway, you can see combinatorially there's a lot of junk here, and so you'd have to like parse it into loop. Each one of these loops is 0, right? And because each one of these loops integrates to 0, you can get that the integral along this part of C1 is equal to the integral of that part of C2. And basically this, you can apply the loop by loop by loop by loop by loop by loop, and then piecing that junk all together, you get path independence. But I don't think students ever challenged me on this. I've usually been able to spread this simplistic lie to students, and they buy it. Or at least they're nice enough not to challenge me on it. And again, I'll postpone the proof of 4 implies 1 till later. Some examples. In electrostatics, the potential energy per unit charge is called voltage. And so to actually calculate the voltage, you integrate from minus infinity to xyz of the electric field dot dr. And so if the electric field of a point charge is given by the Coulomb field, and if you take the origin to be a spatial infinity, you can calculate the potential by doing the integral of like the line from infinity to the origin, so to speak. Well, not to the origin, but to rho, and then you'll get that the voltage is k over rho. This is the Coulomb potential we use a lot in like physics, basic physics. So that's kind of, potential energy is everywhere in physics. You'll see it if you take physics. There's also something very interesting here in that the potential function is not unique, right? Because if you calculate the gradient plus a constant, you still get the same gradient. That means that where the 0 for the potential energy is up for grabs, right? There's an ambiguity in assigning potential energy. And that ambiguity is what's called, well, it turns out it's something called gauge freedom. And it actually underlies many of the more interesting developments in modern physics. This gauge freedom is really the starting observation to getting into something called gauge theory. And anyway, that's all I say about that here. But I hope you enjoyed this, and I'm sorry I have been very cowardly and not done 2 implies 1 today. But again, if you'd like to see me prove that, ask me and I'll find you a video. They exist. So, oh yeah, thanks guys.